Welcome to the presentation video of the Automotive Electronics course intended for third-year students in automotive mechanics. As stated in the previous video, this course aims to introduce the student to the concepts of automatic vehicle control. This video includes the following chapters: Introduction to Systems Control Theory, presentation of the different sensors and actuators involved in the control of the thermal combustion engine, basic notion of electronics and microcontrollers, and finally, the different means of diagnosing breakdowns. Automotive electronics refers to the technologies and systems that regulate and manage the various functions and behaviors of a vehicle to ensure safety, efficiency, and performance. Modern vehicles rely heavily on control systems for everything from engine management to advanced driver assistance. Short presentation of the contents of the first chapter. System control refers to the methods and technologies used to manage, regulate, and oversee the behavior of systems to achieve desired outcomes. It involves the application of control theory to design systems that maintain stability, performance, and efficiency despite external disturbances or changes in operating conditions. Key aspects of system control include feedback mechanisms, using sensors to monitor system output and adjust inputs accordingly. Control algorithms, mathematical models that determine how the system responds to changes. Automation, implementing control processes without human intervention for efficiency and accuracy. Stability analysis, ensuring the system remains stable under various conditions. System control is crucial in various fields such as engineering, robotics, aerospace, manufacturing, and process industries. Introduction of the second chapter. In a thermal engine control system, sensors and actuators play crucial roles in optimizing engine performance, fuel efficiency, emissions control, and temperature regulation. These components work together to monitor and control various engine parameters, enabling the Engine Control Unit (ECU) to make real-time adjustments for optimal operation. Key sensors in thermal engine control. Coolant temperature sensor (CTS) measures the temperature of the engine coolant. Provides feedback to the ECU for controlling the air-fuel mixture, ignition timing, and activating the radiator fan when necessary. Usually installed in the engine block or cylinder head. Exhaust gas temperature sensor (EGT) monitors the temperature of the exhaust gases. Helps prevent engine overheating and optimizes turbocharger performance by regulating fuel injection and ignition timing. Typically found in the exhaust manifold or downpipe. Intake air temperature sensor (IAT) measures the temperature of air entering the engine. Used by the ECU to adjust the air-fuel ratio for optimal combustion, especially under varying atmospheric conditions. Located in the intake manifold or air filter box. Manifold absolute pressure sensor (MAP) measures the pressure inside the intake manifold. Provides data to calculate air density and determine the correct air-fuel ratio, improving engine efficiency and power output. Mounted on or near the intake manifold. Mass airflow sensor (MAF) measures the mass of air entering the engine. Critical for calculating the proper air-fuel ratio for combustion by providing real-time air intake data to the ECU. Usually located between the air filter and the intake manifold. Oxygen sensor, O2 sensor, or lambda sensor. Monitors the oxygen content in the exhaust gases. Helps the ECU adjust the air-fuel mixture to ensure optimal combustion and minimize emissions. Installed in the exhaust manifold or after the catalytic converter. Knock sensor. Detects engine knocking or pre-ignition. Sends signals to the ECU to adjust ignition timing and prevent engine damage due to knocking. Mounted on the engine block or cylinder head. Throttle position sensor, TPS. Monitors the position of the throttle valve. Provides input to the ECU for controlling fuel injection and ignition timing based on throttle input. Connected to the throttle body. Crankshaft position sensor, CKP. Monitors the position and rotational speed of the crankshaft. Provides data to the ECU for timing fuel injection and ignition events. Positioned near the crankshaft or flywheel. Camshaft Position Sensor, CMP. Detects the position of the camshaft relative to the crankshaft. Works with the CKP sensor to time fuel injection and valve timing events. Mounted near the camshaft or cylinder head. Key actuators in thermal engine control. Fuel injectors. Spray fuel into the combustion chamber or intake manifold. Controlled by the ECU to deliver the correct amount of fuel for combustion. Installed in the intake manifold or cylinder head. Idle air control valve, IACV. Regulates engine idle speed by controlling the amount of air bypassing the throttle. Adjusted by the ECU to maintain stable idle RPMs, especially during startup and when accessories like air conditioning are in use. Connected to the throttle body. EGR valve, exhaust gas recirculation valve. Recirculates a portion of the exhaust gases back into the intake manifold. Reduces nitrogen oxide, NOx, emissions by lowering combustion temperatures. Found between the exhaust manifold and intake manifold. Radiator fan. Cools the engine by drawing air through the radiator. Controlled by the ECU based on coolant temperature to regulate engine cooling. Attached to the radiator. Thermostat. Controls the flow of coolant between the engine and the radiator. Opens and closes based on coolant temperature to maintain optimal engine operating temperature. Typically found between the engine and radiator in the cooling system. Variable valve timing actuator, VVT. Adjusts the timing of the intake and exhaust valves. Controlled by the ECU to improve engine performance, fuel efficiency, and emissions. Connected to the camshaft. Turbocharger wastegate actuator. Regulates the amount of exhaust gas that drives the turbocharger. Controlled by the ECU to manage boost pressure and prevent overboost. Integrated into the turbocharger assembly. Throttle actuator, for drive-by-wire systems. Electronically controls the throttle valve position. Adjusts the throttle opening based on inputs from the accelerator pedal and ECU. Mounted on the throttle body. Cooling pump. Circulates coolant throughout the engine and radiator. In some modern engines, it's controlled electronically for variable speed operation, optimizing cooling efficiency. Part of the cooling system, usually near the front of the engine. These sensors and actuators allow for precise control over the thermal management and overall operation of an engine. The 3-Ed chapter is about electronics fundamentals and microcontroller. Electronics is based on semiconductors, which form the basis of microcontrollers and other electronic systems. A semiconductor, such as silicon, have electrical conductivity between that of conductors and insulators. They are the basis of modern electronic components like diodes and transistors. A diode allows current to flow in one direction only, acting as a one-way valve for electricity and is commonly used for rectification, converting AC to DC. Transistors are semiconductor devices used to amplify or switch electronic signals. Microcontroller basics. A microcontroller, MCU, is a compact integrated circuit designed to perform a specific task in an embedded system. Key components of a microcontroller. Central Processing Unit, CPU, it executes instructions and processes data. It's the brain of the microcontroller. Memory. ROM, read-only memory, stores the firmware, program, permanently. RAM, random access memory, temporary storage used by the CPU for data processing. Flash memory, non-volatile memory for storing the program code, allowing reprogramming and updates. Input-output, I/O, ports. Digital I/O, pins used for reading digital signals, 0 or 1, or sending digital outputs. Analog I/O, ports used to interface with sensors or actuators that work with continuous signals. Timers and counters. Timers measure time intervals or generate delays. Counters count external events such as pulses from sensors. Analog to digital converter, ADC. Converts analog signals, e.g., voltage, into digital values that can be processed by the CPU and is commonly used for interfacing with sensors like temperature, light, or pressure sensors. Digital to analog converter, DAC. converts digital data back into analog signals, and is used in applications like sound generation or motor speed control. Communication interfaces. UART, Universal Asynchronous Receiver Transmitter, used for serial communication. I2C, Interintegrated Circuit, allows communication between multiple devices using two wires. SPI, Serial Peripheral Interface, a high-speed interface for communication with sensors, displays, and memory. CAN, Controller Area Network, a protocol widely used in automotive and industrial applications. Applications of microcontrollers. Automotive, control of engines, ABS, airbag systems. Home appliances, microwaves, washing machines, and smart thermostats. Robotics, control of motors, sensors, and actuators. IoT devices, smart devices that communicate with networks and other devices. Medical devices, blood pressure monitors, ECG devices. By mastering both electronics fundamentals and microcontroller concepts, you can design and control a wide range of embedded systems. Let me know if you'd like to dive deeper into any specific aspect. The duration of each chapter is estimated around 3 weeks. A continuous monitoring will be given to the student in order to evaluate their ability to follow and understand the content. So, at the end of this course, the learner will have accumulated the necessary knowledge in the field of electronic control of vehicles. Thank you for your attention and see you soon for new videos.